Hi guys, how are you? Thanks very much for coming. Today we're going to talk to you about a topic called biomimicry. And hopefully this is going to work. Since the dawn of humanity, we've been inspired by the natural world. The landscapes, plants, and animals all around us have not just been an integral part of our lives in terms of survival, they've also been a huge part of our culture. The natural world has been inspiration for countless poems, stories, musical and artistic masterpieces, dating as far back as the first cave paintings in prehistoric times. Yet at the same time, throughout our history, there's been an increasing trend to separate ourselves from the natural world. We've built environments around ourselves that have consciously and actively designed nature out of our lives. I work a lot with students, and 9 times out of 10, when I ask them to show me where nature is, they point out the window. Nature is something that's out there, that you visited the weekend, and we are in here. So today we're going to share with you a concept that will hopefully add another layer to your understanding and how you see the natural world. Something that might allow us all to get a little bit more re-inspired by nature in a completely new way.
Hello? Oh yeah, there we go. Okay, so has anyone ever heard the term something's man-made, something's natural? Okay, so often we get really confused about this idea of man-made and natural. But in terms of biomimicry, we kind of take that argument away because it's a little bit philosophical. We are a species that live on the planet, just like loads of other species, and we are a natural species. So the things that we make and the things that we do are also natural. We adapt our environment to suit our needs. We build houses to keep ourselves warm. We create things to transport ourselves and move around. And so do other species, such as bees and termites. They'll build nests, and they build homes that will also regulate temperature and store water. But where do we get our ideas to build these things? When we look around this room, every single thing was designed by people for us to suit our needs. But where do we get these ideas from? How do we decide what to design and how to design them? So we brainstorm, we research, we look to the past, we're inspired, we come up with different ideas. But biomimicry asks the question, could we actually look to nature and other species for ideas of how to do things? Could we see how they do them, and could we look and see, could we do it in similar ways? On the planet, we believe that we're one of the most evolved species. We've got a complex language, we are able to use complicated tools, we create, have imagination and design. However, we're also one of the youngest. Life has been on Earth for over 3.8 billion years. And in that time, all these other species have found ways to live on the planet sustainably. They don't create waste, they don't pollute where they live. They've managed to do very complicated things like build fantastic structures and networks. We have all of this all of this time of research and design to learn from them. Unfortunately, some species didn't adapt quite so well to their environment, and their designs didn't work. And the evidence then is found in the fossil records of those species.
There's an incredible wealth of knowledge contained within each and every species that has evolved to live on this planet. And they've all evolved in the same context that we face, planet Earth. And they face very similar challenges, like Katie was saying, to things that we face. And we need to remember that we're not the first ones to try and solve these challenges. Life has had 3.8 billion years to get it right, to go through countless trials and errors and evolve really effective solutions. And organisms have done things very similar to things that we need to do, but they're also doing them in a sustainable way that allow them to live on the planet long term. So for example, trees have figured out how to transport water hundreds of feet into the air without the need for pumps that run on fossil fuels. Organisms have figured out how to build really strong structures that are from locally sourced materials that are in plentiful supply that also biodegrade when they're no longer needed. And organisms have figured out how to harness energy without damaging the planet with harmful greenhouse gases and pollution. So this realization that life has found solutions to similar challenges that we as people face has led to the creation of a new discipline called biomimicry. It's kind of a blend of design and technology and science and engineering. When you break it down, The word biomimicry comes from the Greek bios, which means life, and mimesis, which means imitation or to copy. Biomimicry encourages us to consciously look to the natural world for ideas and models of sustainable design. And really, when we start to be faced with a problem, it tells us to ask the question, what would nature do here? What this means on a practical level is designers, engineers, and architects are actually inviting scientists to the design table to try and get their knowledge of the natural world. And what's coming out of this is thousands of new sustainable technologies. It's really kind of game-changing in the world of design and technology. There's hundreds of examples, but Kate and I have just chosen our favorite 6 to share with you today.
Okay, so this is my favorite one. The picture up in the corner here is of a gecko. So geckos, I don't know if anyone has ever seen, geckos are lizards and they kind of run around the floor, they run up walls, up on ceilings, and it's almost like gravity doesn't have any effect on them. Well, they're not able to stick up onto the ceiling because they have like a sticky substance on their foot. Instead, what it is that they have really, really, really tiny hairs, hundreds and thousands of millions of them. And it's down at what's called a nanostructure. So it's, in fact, they're too small to even see with the naked eye. And when those hairs touch against a surface, they create something called van der Waals force. And that force allows them to stick to almost any surface in any sort of orientation. Now, what's really interesting as well is that when they lift, they're also able to lift it up, so they don't get stuck there either, which would be really awkward for geckos if they did. So what have we learned from that? That's interesting. Well, what we've learned is we've learned how to design sellotapes that don't use any glues or toxic chemicals. So they're a lot more sustainable and they're more environmentally friendly. They're also able to be reused and used on almost any surface and in different environments. We've also learned how to make bandages that don't need clips to stick together, and they can also stick and stay together when it's wet, which is extremely important for hospitals working in emergency conditions or ambulances working outdoors. Then also on a slightly more, I suppose, fun side of it is that if anyone ever saw the Mission Impossible 3 film, they designed the gloves that you can actually climb a building with, sort of like Spider-Man, essentially. So it's always fun.
The little bird pictured here is probably one most of you might be familiar with. We have it in Ireland. It's called a kingfisher. And the kingfisher is a beautiful little bird, but it also happened to be the inspiration for a team of scientists and engineers in Japan who had a kind of a unique problem. They had developed the Shinkansen, which is a bullet train. It's the train pictured here on the right. And it goes 200 miles an hour, so it's incredibly fast. And the trouble was, as these trains were going through tunnels, they would create a kind of a pocket of pressure, of air pressure ahead of them. And when they emerged from the tunnels, there was like a loud kind of thunderclap of noise. And this was really starting to get on the nerves of the people that lived around the tunnels. And as a result, they were complaining, and the train company had to slow down every time they went through a tunnel, which cost the company money and also made train times a bit longer. And the chief engineer of this company, he happened to be an avid bird watcher. That's what he liked to do in his spare time. And he looked to the natural world and to the bird world and specifically to see if there was anything that could inspire him, something that flowed from one kind of pressure difference to another. And he came upon the kingfisher. So the kingfisher, if you don't know, it dives to get its food. It gets little fish. And it has to be really stealthy to actually get the fish. And so what it's done is over time it's evolved this particular shape of its bill in order to allow it to glide into the water without barely creating a ripple at all. And so this chief engineer, what he did was he redesigned the front end of the train to mimic or copy the kingfisher's bill. And I think it's cool because he even put the lights on the train where the little nose holes are on the bill. And not only did this cut down on the noise problem, they didn't have the noise problem anymore, it also allowed the train to go 10% faster on 15% less electricity. So it was saving the company money as well.
Okay. Hands up, has anyone ever seen this creature over in the corner? Impressive. Okay. Very good. So this guy is called a tardigrade or a water bear. He's a microscopic organism. There are probably a few living outside in the grass. They're actually really cool. They're tiny and not hugely interesting to look at, but they can survive almost anywhere. They can cope with being boiled, with being frozen, they can manage to take 500 times the amount of radiation it would take to kill us. They can live in the deepest trenches of the ocean, in the Arctic Circle, and even in the vacuum of outer space. How they do this is that they can dry themselves out and leave themselves in a state of suspended animation. This means that just with a tiny drop of water, after decades, they can just pop back to life and be happy out. They just need a little kind of bubble of water, very small, to survive. So scientists were like, well, that's interesting, but how can we learn from that? How can we use it to our advantage? So they took it and they applied that principle to vaccines. Vaccines often have to stay cold, and they often have to stay cold along when they're getting to the places where they're needed most, which is usually in developing countries. And often the cold chain can break down because of irregular electricity supply or the amount of travel that it has to do. But what they've learned to do is actually dry out the vaccine and then use a solution to reanimate it when it reaches its destination. And they're having much more success in getting vaccines to where they're needed most.
Hands up who's seen this species before? Probably a good lot of you. It's a humpback whale, and if you don't know, humpback whales are huge. They're about the size of like a double-decker bus. They're about 50 feet long, they weigh 80,000 pounds, they are massive. But they're actually very quick and efficient underwater. They can turn really tight circles, about kind of 5 feet in diameter. And they do this because that's how they catch their food. They catch herring, which is a fast fish. And what they do is the humpback whales work together like as a team. And they all circle a school of fish and they blow out loads of bubbles. And they kind of confuse all the fish and create like a little ball of fish that drive them up to the surface and then they eat them. And there was a scientist in the US called Dr. Frank Fish, and he was studying these whales. I thought it was funny as well, fish. He was a marine biologist and he was studying these whales and he was asking how they were able to turn such tight circles even though they're massive. And he realized it was to do with the shape of their flippers. So you can see in the picture here, they have kind of like a bumpy edge along the leading edge of their flipper. And this really allowed the whales to get like a better grip on the water. And it was reducing drag for the whales by up to 30%, which was great. And Dr. Frank Fish decided to apply this knowledge and start a company, and he created something called Whale Power. And Whale Power develops blades for wind turbines. So your traditional wind turbines, they just kind of clip onto the edge of that. And not only do they allow wind turbines to be put in places that aren't so windy, which is a problem at the moment, they have to be in very windy places, they also cut down on that eerie noise that a lot of people don't like about wind turbines, and they're much more efficient as well.
Okay, I've just been told we have 2 minutes, so we're not going to get through all of our examples, so I'm going to say this one really quickly. This is a locust, and locusts are able to basically move within swarms. There's hundreds and thousands of locusts within a swarm, but they never bump into each other. And based on this, it's due to a large neuron at the front of their brain. And essentially based on this ability, Volvo have been developing crash avoidance technology, so they've actually learned how to do this from looking at the locust. So we're going to go next one.
I'm going to fly through this, but I have to tell you because it's my favorite.
Very quick.
This yellow goop on the screen is something called slime mold. It's a very basic, it's not actually a mold, it's a single-celled organism. It has no brain and no nervous system, very basic. And when food is in plentiful supply, it exists as a single-celled organism. But when food is running out, it kind of joins together and creates this like super organism like you can see on the screen. And there were some scientists in Japan studying slime mold, and Japanese scientists tend to be a bit wacky. And what they did was they did a fun experiment. They put a petri dish of slime mold over the top of the railway network for Tokyo. And I have a quick video. We won't probably be able to watch it all, but I'll explain it as we go. So the yellow stuff in the middle is the slime mold, and you can see it grows out in kind of all directions at the same time, okay? It has no brain, so it's not thinking about it. And when it finds a piece of food, so the white dots are representing food, they're representing the stops on the underground railway network of Tokyo. When it finds food, it concentrates its growth in the shortest path between them, and it retreats from anywhere it doesn't find food. And what happened is, the slime mold had perfectly recreated the map of the underground railway network of Tokyo. This was a problem that took teams of scientists and engineers over 3 years to come up with. Slime mold did it in 26 hours. 26 hours with no brain and no nervous system. And I think that could probably be applied to the Lewis. It'd be very helpful for Dublin. Okay, so biomimicry is very exciting.
Yep.
Not only does...
I'm afraid
Are we done for time?
We got to go, I think.
Yeah, all right. It's very exciting.
Just want to say thank you guys for listening. That we run workshops on this. If there are any teachers that are interested, feel free to come up and get us afterwards. There's also a huge amount of resources online that you're available if you're interested in the subject anymore. You can check out. Thanks a million.
Thank you.